Hi everyone, so this is a tutorial for homework number 2 of cell engineering, and this homework focuses on the MapK cascade, and it's based on this paper, which I would recommend reading actually before you watch this video, and you should definitely read it before starting the homework. And in the code you're actually going to be recreating some of the figures from this paper. So I'm gonna go through some of the template code with you and then go into a little more detail on some new functions that you may not be familiar with. So to start in the code, if you look, you have this list of all these molecule names, and these are all the molecules involved in the MapK cascade. So again, if you look at the paper, here you have this list of all of the reactions involved in the MapK cascade. So this list of molecules corresponds to all the molecules in all of those reactions. And then this vector sets up all of your initial conditions for all of these molecules. So this vector, the order in this vector corresponds to the order of the molecules in this list. So for example, the initial concentration of MapK, which is number 3 in the list of molecules, corresponds to the third value in this vector. So the initial concentration would be 1.2. And for example, you can see all of these values are 0, which correspond to these complexes. So initially, before any reaction has occurred, there's not going to be any complexes that have formed. And similarly, if you look at the fifth value in the vector, which corresponds to the MapK pp concentration, it's 0. So MapK pp is the double phosphorylated MapK, which is fully active. And again, there's not going to be any fully activated MapK before any reaction has occurred. So in the next part of the code, you're basically going to be recreating figure 2 from the paper. So for various input stimuli, you're going to be determining the steady state activity of MapK, MapKK, and MapKKK. So if we go back to the code, so points is going to determine the number of different steady state points or different stimuli that you want to, different input stimuli concentrations that you want to evaluate. And then here, if you're not familiar with this, this is basically just setting up an array that has points, number of rows, and 3 columns, but is all zeros. So that's something that you'll see a lot where people initially will create an array of all zeros. So it's basically an empty array that then you can put values into later. So then here so if you're not familiar with this syntax, the colon is basically saying I'm going to call all the rows of stim, the array stim, but only the first column. And so I'm going to set the first column to log space, and then you have to put in the values here. So this first column corresponds to the stimulus range for MapK, and then the second column is MapKK, and the third column is MapKKK. And as it says here, MapK has a narrow range, and then MapKK medium range, and MapKKK has a broad stimulus range. And then you can look at figure 2b here to kind of inform what stimuli ranges you want to use. Okay, so in the next part of the code, we're actually going to solve for the steady state enzyme concentrations for MapK, MapKK, and MapKKK over the stimuli ranges that we just defined earlier. And we're going to use an ODE solver to solve a system of equations. And the ODEs have been defined for you in the paper here based on the reactions in the MapK cascade. And then all of these ODEs have been put into the code for you already in this evaluation function. And so Y is basically an array that has the values of the concentration values for each molecule at various time points, and the Y is in the same, the molecules are in the same order as they're listed above. So as they're listed here, so the same order as Y0. So we're going to use the ODE solver ODE23S, and it takes three inputs. The first is the function that has the ODEs. The second is t-span, which is the range of time over which we're going to integrate, and we've already defined t-span above. And then the third is our initial conditions, which is the vector y0. And then it's going to output t, which is a vector that has the range of time, the different time points that it evaluated over the range t-span. And then the second is y, which is going to have the concentrations of all the different molecules at each time point. So we're going to use the ODE solver for MapK, MapKK, and MapKKK. And for each enzyme, we're going to solve the ODEs for all the different input stimuli concentrations that we defined earlier. So to do this, we're going to use a for loop. For those of you who don't have any coding experience, a for loop basically just repeats a segment of code a specified number of times. So just as a really quick, very simple example, if we define x as 0, and we said for p equals 1, 2, 5, x equals x plus 1, and every time you have a for loop, you have to write end to close it. So basically it's going to run x equals x plus 1 5 times, and each time the loop runs, p is going to go to the next value. So it starts at 1 and then keeps increasing, and the loop finishes when p is equal to 5. So going back to the code, so this for loop is basically going to run these 4 lines of code for every point in the for every different stimulus concentration that we defined above. For every point in the first column of stim, which corresponds to all the different stimuli concentrations we wanted to test on MapK, we're going to run the ODE solver and figure out what the steady state concentration is at that input stimuli. So the first line is basically setting the initial condition of the input stimulus. So the second value of y0, if we go up, corresponds to the concentration of the input. So we're just here setting that value to one of the points in stim. Here we're running the ODE solver, and then so this is going to give us the concentrations of the molecules over various time points. But we're really only interested in the steady state enzyme concentration, which is going to be the last value. So it's going to be the concentration of MapK pp at the longest time point. So here we're taking the length of the first column of y, which it doesn't really matter what column it is, but we're basically taking the length of y, and then we're calling the last value, the last time point of y in the fifth column. And we're looking at the fifth column because if we go up again, the fifth column is going to correspond to the concentration of MapK pp, the fully activated version of MapK, which is what we're interested in. So yeah, this is just we're putting into this array V that we created above the value of the concentration value of MapK pp at the longest time point, which is the steady state enzyme concentration. And then you're going to repeat this for MapKK and MapKKK, and it's the same exact thing, but you're just going to obviously change some of the values accordingly. So now you have all of the steady state enzyme concentrations for across the different input stimuli. And the next thing you should do is we recommend that you normalize the enzyme concentrations by the max concentrations, as is done in these graphs. So basically the y column is going from a relative steady state activity from 0 to 1. Like 0.1 corresponds to 10% of the maximum activity, 0.9 corresponds to 90% of the maximum activity, 0.5 corresponds to 50% of the maximum enzyme activity. So you can do that by dividing each column by the last value in that column of V. So the last value in each column is going to have the steady state concentration at the highest input stimulus, which is going to correspond to the highest steady state concentration. So the next thing that we recommend that you do is use interpolation to find the EC10 and EC90 points, which are the input stimuli that correspond to a 10% and 90% 10% and 90% of the maximal response, respectively. So we suggest you use spline to do this, which is a function that performs cubic spline interpolation. And if you look up spline MATLAB, you can find the page that has more information. But basically, you use spline to estimate the value of a function when you have a discrete set of points. So just as an example, let's say we had a function that was x equals 2y, but we only have a discrete set of points. So we have x equals 1, 3, 3.5, 6, 7, and we have y 2, 6, 7, 12, 14. So obviously in this case we know that x equals 2y, but let's say we just had these points and we didn't actually know the function that it corresponded to, and we wanted to estimate what y is equal to at x equals 2 and x equals 4. You can put in spline x, y, and then the values that you want of x that you want to estimate, and it gives you y equals 4 and y equals 8. So you can also switch y and x, because in this case we actually want to estimate the values of x for certain values of y. So we want to estimate the input stimuli at 10% and 90%. So in A and B you would be putting 0.1 and 0.9. And then you can do the same exact thing to find the EC50 points, so you don't have to put in 2 points here, you can just put in 1 point. So in the case of EC50 you would be estimating the values of y at x equals you would be estimating the value of x at x equals 0.5. And for all of these ECs, you're going to do it for all 3 enzymes. The next thing you're going to do is calculate the Hill coefficient, and the equation is in the lecture notes. And again, you're going to do that for all 3 enzymes, and you should hopefully get something somewhat close to the values in figure 2b. They're not necessarily going to be exactly the same, but they should be close. So next we're going to make all the plots. So this first plot is just all of the concentrations of all the enzymes over time, or not of all the molecules over time. So it's already plotted for you. You should just add legends and axes titles. So next you're going to recreate figure 2b from the paper, which as a reminder is this figure that is on the x-axis is on a log scale. So as a result we're going to use semi-log x, which you should be familiar with from homework 1. So you're first going to plot the map k values, and then map kk, and then map kkk. These 2 lines are just going to plot these two lines here. So it's going to plot just a line that goes across the plot at 10% of the maximal value and one at 90%. And then we're going to recreate figure 2a, which take a note that the x-axis for figure 2a is the input stimulus in multiples of the EC50. So you're basically going to want to divide your input stimulus by the EC50 for each enzyme, and that should be your x-axis, or that should correspond to your x values. And then that graph is not in log scale, so you're just going to use the regular plot function. Oh, and I should just mention, in case you don't know, this just defines the color of the line. This is going to make, the default is just that the line will be black, and then the second line will be red, and then this line will be green. And yeah, if you look up like plot or semilog x on Google, you can find the letters that correspond to all the different colors that they have. Okay, and then finally, you want to add to figure 2a these overlays, which is the dotted lines here that correspond to the Hill equation curve. So you've already calculated the Hill coefficient for each enzyme, and then you're going to plot basically the Hill curve that corresponds to that Hill coefficient. So again, we have the Hill equation is in your lecture notes, so you should use that. And as a recommendation, you could use a for loop to basically figure out the Hill curve for each of the three enzymes. So you can create an array that has where each column corresponds to the Hill curve for each enzyme. So just as a reminder, you want to make sure that all of your graphs have a title, a legend, and axes labels. And you're going to basically plot a lot of these figures again, but with some perturbation of the MapK cascade, which is up to you. So yeah, that's it for the template code. Hopefully this helps, and good luck with the homework.